All right, so my name is Nicolas Silva, and I work at Mozilla Paris as a graphics engineer. So I work on basically the graphics engine of Firefox on every platform. And the subject of the game industry is really close to my heart because maybe as many of you here, I wanted to make video games. I spent a few months at Ubisoft on an Xbox 360 title as an internship, and then I discovered open source and I decided to go for the browsing industry. But I really like video games, and especially making them. So today I will talk about the gaming industry and the web, which is sort of like the theme of this entire conference thing. So. As an introduction, today, targeting different hardware is a terrible experience. It requires a lot of work. Platforms, they try to differentiate, so they offer different APIs that are like better or like nicer to use or faster or more this or that. But in the end, it requires you to write a lot of code for specific to some platforms, and platforms get left out. Like Linux or from a market share point of view, the equivalent of Linux on the mobile space, probably Windows 8, right? And we want to make games that run on all of those platforms, right? Moving to new platforms, it requires to adapt your technology, to acquire new skills. It's a lot of efforts, And you also have the problem of the distribution platforms that can, that control what you can put on their platforms. For instance, I want to make this iOS game, and suddenly the terms of the marketplace changes, and I can't distribute my game on the iOS anymore. That's not really a great experience, right? It's not a very comfortable thing to build a game business on, right? And seriously, it's 2014, and we're still in this model where you have to install apps before you can try them out. I think it's sort of, it was already the case 20 years ago, and we should be hoping that, those things change, and that we can, just like when you go buy some clothes, you look at the clothes on the shelves and, oh, it looks good. I want to try it on. And so, you try it on. If it fits, if it looks good on you, then you buy it, right? I want this to be the same for apps and games. I want to try a game and then install it if I like it. But, that's the state of targeting different platforms and a lot of those platforms today. And ask yourself this question. Do you want to make a game? Or do you want to make a game for a platform? I mean, you might love Android and be like, oh, I want to make a game for Android. But I think that most of you guys are interested in making a game. So the platform should really be something that lets you, it's a technological stack on which you build your game. It's not something that should restrict you and impose costs and stuff like this. So yeah, making games today on a lot of platforms, it's not the greatest experience. So how about making a web game? The web runs on a lot of platforms, on mobile, on the desktop, on TVs soon maybe. We even have operating systems built entirely on the web. So how about making web games, right? But some industries haven't yet made a massive move to the web. And I'm thinking about the game industry, and more specifically the AAA game industry. We've seen some really, really cool demo with Unreal 3 and soon Unreal 4. But right now, we mostly have demos. We have one game that's been released that runs on the web with Unreal. I want to see more of that coming. And a lot of the game developers, when I asked them about why not, move to the web, they have a few. There are a few things they tell me sometimes, and often it's the same three problems. As well, I don't know. Like the web wasn't meant for high-end games. JavaScript is too slow. It's sort of a hack. I disagree. And also there's this valid point. I spent 10 years building my business on this technology that is written in C++ that I invested in, and I just don't want to rewrite everything in JavaScript. And I might not have the skills to do the high-end game engine in JavaScript because I specialized in C++ my entire life. Okay, don't worry, we have a solution for you. And also, there is the I need to access the hardware. I want to access the camera. I want to add some stuff to my game, like when the phone is shaking like this. I want to react in some ways. And yeah, sometimes APIs are missing, and I'll show you that we're working on that. So to address the first comment. Let's talk for a little bit about how the usage of the web has evolved. At first, the web was very static. It was just a bunch of text and some hyperlinks, and it was already great. You could access information everywhere, and it was awesome, but it was not enough. And so people made the web more dynamic, and once things started getting dynamic, people were like, oh, cool, I can make services on the web. I can make a Make client, an e-shopping platform, and a lot of stuff like this. And then those kind of software actually mostly run on the web these days. How many of you use a web client for their emails? Just raise your hand. Most of you guys. Okay, right? So the web already has sort of won that battle. If you can call it a battle. Anyways, a lot of people are building software on the web already, but it's mostly kind of static content, dynamic because you interact with the server. We need more interactivity, so boom, HTML5 comes in. Buzzwords, buzz logos. There's this strong push to get more APIs in the web, and to make the web more interactive, make it like a first-class application platform. And I'm still amazed at the amount of PR that went into HTML5. It has its logo. It has a bunch of other logos that you can find in my slides if you recognize them. I sort of rediscovered that when I was looking for stuff, to spice the slides. Anyways, back to HTML5. So the web becomes an application platform, and it's interactive, it's dynamic. What's the next step? Well, now we want to build operating systems on the web. And Firefox OS is one of the examples. There's also Chrome OS, and other I've tried, other will come into this market, and I think it's an exciting thing to get into, and I'll talk about why a bit later. So what I want to show you there is that the web has evolved both in usage and in its capabilities in terms of APIs and stuff like this. And just like the web, browser technologies have evolved quite a bit. And that's actually a big deal, because a lot of the complaints that I get are, oh, well, I've been using browsers for 20 years, and they're too slow to make my AAA game. I need to do this and that, and it's not going to run in the browsers. Guys, browsers are evolving really, really fast. I can tell you that because I work on the internal of one of those fancy browsers that you guys probably use, right? So the internal architecture of web browsers is evolving really fast. If I can give you an example for, the browsers at the beginning were here to display static content, as I said, and so they were built around this massive event loop that was just doing everything, run the layout, run the painting, and compositing and everything, like all the rendering of the web page. And now we're moving away from this and making more things, parallel and asynchronous, and like splitting things, sandboxing web pages and things like that. This is quite a massive amount of work that goes into making turning browsers that were document presentation platforms into application development platforms. And this is something that we've been doing for years and that we'll keep doing. So if there's one message that I can pass right now, it's don't stay, your image of what the web is should not remain this. It should be more like this and whatever comes next. I don't know yet, right? The web will evolve and web technologies will evolve, and the web industry is pretty active and pretty dynamic. So things are moving. And as an example of how far we want to research and improve this kind of thing, Mozilla Research is working on an experimental browser engine that is called Servo, that is written from scratch in a totally different language. It's not even written in C++. It's written in Rust, which is a language also developed by Mozilla Research. And they're experimenting with crazy things, like computing the layout of a web page on the GPU. It might not pay off, we don't know, but at least we have some playground to experiment with things and see how we can have the perfect application platform for the future. And now let me talk a little bit about JavaScript, because JavaScript is at the center of everything on the web now. You all know the story. It was made in 1 week, and it wasn't really designed to be a very fast language at first. I give you that. But and also, it's called JavaScript. It's a scripting language, but today the way people use JavaScript, it's not really a scripting language anymore. It's a full first-class programming language. It's the programming language of the web. And a lot of effort, and engineering effort, research and development goes into making JavaScript really fast. So the performance of JavaScript a year ago is really not the performance of JavaScript today. I'll probably talk more about how JavaScript works. I actually don't work on the JS engine, but I have a few insights. It depends on what you guys are interested in. I'll ask a few questions afterwards, and I'll leave some room at the end for questions. I don't think my presentation is going to last 1 hour. So where was I? Yeah, JavaScript. JavaScript is this wonderful language that lets you do amazing things, also lets you shoot yourself in the foot, and lets you do really fast things if you restrict yourself to a subset of the language that we know is fast and easy to optimize for JavaScript virtual machines. And it's also a language where if you use all the dynamic and fancy features, you might generate some very, very slow code. So once again, don't think JavaScript is slow because you've wrote something in JavaScript and it wasn't really fast. That's the thing. Nowadays, if you want to do top-notch things on the web, you need to be good at writing JavaScript and understand how to write very fast JavaScript. And many of you maybe have read JavaScript: The Good Parts. It's this tiny book, when you compare it with the JavaScript book, and then the good parts are there. But the good parts are really good, and they allow you to write really efficient programs. Now, speaking of subsets of JavaScript, game developers and other industries needed to write very, very efficient code, like stuff that could process a lot of things on the client side. And so people needed a way to write some JavaScript that was reliably fast. When I say reliably fast is I write code and it runs on my hardware, and I run it on someone else's computer that is roughly the same hardware, and it should run. You shouldn't have big differences in performance profiles. It's kind of a big deal because you want to distribute games Well, you gotta know what kind of hardware you recommend for your game and what kind of performance people should expect with like a certain class of hardware. So reliably writing efficient JavaScript code is a big deal, especially for the game industry. And what Asm.js is, it's just a subset of JavaScript. It's a very, very restricted subset of JavaScript that doesn't do things that are very hard for browser engines to optimize. So if you restrict yourself to Asm.js, you have something that runs really, really fast on most browsers. And so it's a spec. So browsers, implementers can, look at the spec and implement specifically things for Asm.js. And then you can get something that runs at full speed. And when I say full speed, it's like between 1 and 2 times the speed of like once or twice slower than native speed. Like worst case, you get like twice slower, which is incredible on the web already. Oh, that was fun. There's some wood. All right. Anyways, sorry about this. So it's a spec. Every browser implemented can optimize for it, but they don't have to. They can just run JavaScript, and it's compatible. So one nice thing that you have with Asm.js is that you write some code for Asm.js. It runs super fast on Firefox because we optimized the crap out of it, and it's also going to run well on other browsers. And it's not only optimized in Firefox, actually, because at some point, Google Chrome and Opera followed us in the adventure. And thank you guys for doing that. I mean, that's great. I think we need more people to optimize for Asm.js so that people can deploy very fast games on the web. And I think now it's time for other browser implementers to join the party. So we estimate that 75% of the gamer community uses browsers that are optimized for Asm.js, which is kind of pretty cool because it's already like a lot of installation base if you want to deploy your game that uses Asm.js. Now, Asm.js is not as nice to write by hand as JavaScript, like plain JavaScript. I mean, you can do it. There was this company that made the Orbex.js, the Orbex.js video decoder that runs in JavaScript. I think the name is Otoy, and they hand wrote JavaScript code that was really, really fast, and it was actually pretty much Asm.js. Like a guy from the JS team at Mozilla came to them and said, like, you should add the use ASM directive at the top of your file, and it's just going to be blazing fast in Firefox. So yeah, it's not great. It's not great to write by hand, and you probably want to generate Asm.js code. It's much easier. So I was actually not looking at my slides. I'll come back to that later. Asm.js, it's based on JavaScript, and I think it's a big deal because everybody already runs JavaScript, and we could have tried to specify a bytecode format for the web, just like Java or probably native client, although I don't really know well the details of native client, but I think the first native client is some sort of x86 virtual machine, and Pinnacle, like the portable native client, is more close to LLVM or something like this. We think that we should build the web on top of what it already has, and JavaScript is one of the strong things in the web. And we think that building on top of JavaScript is important. So, why not use bytecode like LLVM? Well, let's talk about LLVM. I love LLVM. It's a great compiler toolchain. I mean, that's what I used to build Firefox, but it was not designed to be a bytecode for runtime. And so, you know, the bytecode is a little bit verbose, and the virtual machine itself, the LLI virtual machine is like 20 megs. We can't afford to add 20 megs to Firefox like this. We have numbers that show that when we add 2 megs to the executable Firefox, we get less installs per day. That's actually a big deal for us. So why add a bytecode specification when you already have something that works with JavaScript, right? What does the bytecode provide us anyway that we don't have with ASM.js? Another thing that is worth noting is that when you specify a bytecode format, you specify something that is really low level. And that doesn't give browser implementers a lot of freedom to optimize, because you pretty much specify how things should be at the low level. And I'll give you an example. So IronMonkey takes an internal bytecode format that you know, like the JS team designed specifically for how IronMonkey works, and it's like homemade and all. And it takes this bytecode format and it turns it into the control flow graph, and then generates binary out of this. So that's one way to do the thing. V8, for instance, does things differently. It directly generates an AST, and from the AST, derives the control flow and straight to binary. So while we're using internal bytecode, they're using ASTs, and in the future, we might want to move to an AST representation. A V8 might, you know, want to move to a bytecode representation. The point here is that we have the freedom to look for the best solution, and this freedom comes because the JavaScript spec is pretty high level. So we have a lot of room to implement the best solution for it. And if you freeze the standard on something that is very low level, then you end up making choices that you will have to stick with for the next 20, 50, a billion years if the web and the human race sticks that long. So, yeah, we think we should build on JavaScript, and so we made ASM.js. And I think we've proved that the performance of ASM.js are pretty good and comparable to native. So we don't think we need a bytecode specification for the web. Now, I was talking about handwriting ASM.js code, and that's not the best experience, and most people will want to write code in a language and export, like compile to JavaScript. And I say compile because the actual word is transpile, but it's kind of an ugly word, and people understand the word compiling, so that's what I'm going to use throughout this presentation. So people like, you know, Unreal, and most of the game industry use C++ for games. And so these guys, they're like, oh yeah, we want to use the web, but we're not going to rewrite everything in JavaScript. No way. There's a lot of technology that we invested on. And so we built tools to generate JavaScript code from C++ code. And this tool is called Emscripten. Emscripten takes LLVM IR bytecode. So IR stands for intermediate representation. So it's this in bytecode format that LLVM has, and that you can run, you know, optimization passes on, and then you have a backend that generates binary format. That's what Emscripten uses. It takes this LLVM IR code, so you can run all the optimization passes, and then we take it and we output JavaScript. But what that means is that it's not restricted to C++. You can take any language that has an LLVM backend and like write a little bit of glue and and then use Emscripten to output JavaScript code. And that's kind of nice because not everybody here is into C++. Maybe it's the language of choice by the game industry, but I don't know. Like other people might be interested in different things. Emscripten generates asm.js code, so it's blazing fast. We get performance that is close to native. That's what the Unreal engine is using. Actually, they're using Emscripten to take the the C++ engine, their entire technology, and just output JavaScript. So Unreal Engine 3 was announced a year ago, and everybody was like, "Wow, so great!" And the Unreal guys were so excited about this that they immediately said, "Oh yeah, we want to keep working with you guys and work on asm.js and Emscripten for Unreal 4." So I don't actually have an Unreal 4 demo to show you today, but I encourage you to follow what's going on GDC, which is next week, because there are going to be some cool stuff there. So yeah, Emscripten, asm.js, really awesome. It also generates very compact JavaScript, which is kind of a big deal if you want to pass a big game through the network. You don't want very verbose representation of the program because you can be bandwidth limited. And also, I'm kind of like selling Emscripten. It's super cool. It's what we made at Mozilla, but it's not the only tool. If you want, you can also evaluate Mandrill and Duetto. Mandrill is not open source, unfortunately, but it's pretty similar to what asm.js does. Like the kind of code that it generates is sort of similar. Well, Duetto has a completely different approach. It's specific to C++, and they generate actually human-readable JavaScript that uses like JavaScript objects and stuff like this. So you probably won't get the same performance profile. It's a trade-off. I think it's really great that we have several tools so that people who want to build business on top of this kind of technology get something like they're not stuck with one technology that could like get deprecated somehow. Many of you are probably interested in how asm.js works. And I haven't really made specific slides about this, so I'm just gonna back out a little bit and talk about JavaScript for 5 minutes. Who knows what a just-in-time compiler is? Raise your hand. Okay, half of you guys know. So basically, a just-in-time compiler is it's an interpreter that compiles code as it's executed. So the idea here is that when you run the code, you can collect information about how the code is used, and that's pretty important with a language like JavaScript, which is very dynamic, and you can write this function, and you don't really know if it's going to take a number or a string or anything when you parse the code. But when you run the code for a while, you can notice that, oh, this function has been run like 100,000 times. It's probably time to optimize it. So we're going to compile it down to binary, and then it's going to be like faster. And this means that if you write a function in JavaScript that always takes numbers, and that you call it quite a bit, it's very likely in modern browsers to be compiled down to binary during the execution. However, if you call the same function again and pass it something that is not a number, like a string or like an object or something, suddenly the engine is going to have to do what we call a bailout. It's going to say, oh, this doesn't work with the binary version that I've optimized here, so I'm just going to throw away the compiled version and go through the slower execution path. And maybe at some point later, we'll optimize it again. So why am I saying this? It's because asm.js code basically restricts you to a subset of JavaScript where you pretty much know what kind of objects you're passing to functions. And it helps JIT compilers do their work properly. So even with browsers that do not optimize for ASM.js, ASM.js actually tends to be a JavaScript that is very, very, very easy to JIT. And so it generally gives you much better performance in browsers that don't especially optimize for ASM.js. Another aspect of using ASM.js and Emscripten that you might be interested in is that the game industry, especially the C++ gurus that make AAA games, like to manage memory at the lowest levels and write code that is very cache efficient. Because when you do a lot of processing, you really need to work well with the cache. And when I say cache, I say like the CPU cache, not like browser cache or anything like this. And that is mostly done through data locality. It's better to go through an array of contiguous data when you're processing things one by one than like jumping around in memory. The performance are very, very, very different. Like you guys should try it out. Like start writing some C++, make a very big arrays of numbers that you do some non-trivial or even trivial operations on. And then do the same thing with an array of pointers to numbers that are scattered around in memory, that you just allocated without paying attention to memory locality. So JavaScript doesn't actually let you control memory that much. And so when you want to optimize things and do data-oriented designs and stuff like this, which the video game industry likes, well, you really need some way to ensure that the layout of the memory is what you expect when you write your C++ code. And the way Emscripten works is that instead of allocating JavaScript objects, it uses big typed arrays. And there you go. You have this guarantee that typed arrays are contiguous in memory, and that when you write like C++ code that goes through Emscripten, you have the same alignment and memory locality guarantees that you have when you generate C++. And when you want to write a AAA game, that's a big deal. The performance of the Unreal Engine would not be the same if they couldn't have this guarantee of cache efficiency. I know that a lot of web developers are not really familiar to this idea of cache efficiency, so sorry if I lost you guys. Don't hesitate to ask questions in the end. So you guys all know what WebGL is. We've had a pretty cool demo in the previous presentation. Really kudos. It was really impressive, and in particular, I really liked the fact that there was this care of having tools and like integrating toolchains in the Babylon engine. It was pretty cool. So I'll definitely check it out. Anyway, so I'm not going to talk too much about WebGL because you guys all know what it is. You've seen how powerful it can be. I just want to underline the fact that WebGL is really low level. It's not your usual, your nice to use web API, or usually like the specs try to be nice for web developers and accessible. WebGL is actually kind of like a grown-up API, and if you want to use WebGL efficiently, you need to understand how GPU works. So, so if it's not your thing, I encourage you to use the cool libraries like Babylon.js or 3.js or a lot of other alternatives. So how does WebGL work? Well, on platforms where WebGL is known to work well, that is not Windows, WebGL is pretty much WebGL calls and then a security layer and then your driver, basically. It's a very, very low-level API, so the performance characteristics of WebGL are going to be roughly the same as when you write, like handwrite OpenGL code in C++, and that's kind of a big deal as well, right? You get the same kind of performance. The only overhead that you have is the security layer, and security is actually a big deal on the web. I don't want a spec on the web that let websites control your computer, or like read the content of your Windows, or spoof your keyboard and stuff like this. So security is a big deal, and I'll talk about it a little bit, and if I have some time. So what I just wanted to outline here is that WebGL is really fast when the hardware is really fast. It's really what you expect from normal OpenGL plus a little bit of security. Another thing is that most of the web APIs go through the W3C standardization process, etc. And WebGL does that as well, but it also has the same extension model as desktop OpenGL and mobile OpenGL, which means that the new shiny OpenGL extensions tend to arrive faster than if they were going through the entire process of being standardized. And then what happens is when we want to upgrade the WebGL spec, like we're working on WebGL 2, then we look at the existing extensions, we pick the ones that we want to standardize and make part of the core profile, and then we say, okay, if you have WebGL 2, then you have all of these extensions. And that means that WebGL 2 is not out yet, but you can already play with fun stuff like multiple render targets. If you want to make AAA games, and you need to do some super cool differentiating effects and stuff like this, you probably want multiple render targets. And it's not part of WebGL 1, but you can load the extension. It works in Firefox at least. I haven't checked for the other browsers, but there probably some form of support. When I say it works in Firefox if the driver implements the extension itself as well, right? So it also depends on the hardware. So you've got to do some form of feature detection. And array instancing, all the cool stuff. Okay, I need to get a bit faster. So I'm going to pass on the demos because you've seen some really cool stuff, and apparently the network doesn't like me too much. I'm also going to pass on WebAudio. WebAudio has been pretty much designed for the game industry, so yeah, pretty much it covers everything you need to make games. And now it's in Firefox, it's in Chrome. And when you need to access other kinds of hardware, we have a lot of APIs that we are trying to standardize, that we are standardizing, that are already standardized, and that are going to be standardized later. Basically, if you guys think there is something that you have on your phone and that you don't have in the web API, it probably means that someone is working on the spec to get the web to party with the native platforms. It's just requires sometimes some time to get in the implementations themselves. A quick note about distributing games, because that's also a big deal. And why are we interested in making games for the web? Well, there's the the web is cross-platform, and that's awesome, but it's also a great distribution platform. Why is that? Well, the web is a standard platform. It means that there are a lot of actors that are working together to build the standards. And what that gives you is APIs that haven't been designed by one entity. It also gives you the more insurance that the design, like the API is going to stick around for a while. It makes the standardization process a little bit slower, of course, but you tend to have higher quality APIs because designing APIs is hard, and you better have a lot of actors working together to get the best APIs. And we're not in the world where browser implementers try to differentiate by giving you different APIs. Now the consensus is that we want the same APIs everywhere, and now the way to differentiate is to have the best implementation of this API. So you guys have known a web where, you know, like browser X was like saying, oh yeah, we added this, and browser Y was like, oh yeah, we have this counter proposal and we added this, and then standards body like 2 years later would just come and be like, oh man, we have 2 standards and it's used all over the web, and now we kind of like need to decide which should be the standard. Like people don't do that anymore. Now people work together, and that makes for a better standards and a better experience for web developers. The web is an open platform, and I say open because the standardization process is open. So you're in the game industry, you need stuff like, you know, features in web audio. Well, you can take part in the process of standardizing the web audio API, and that's actually what happened. Basically, the web audio API was designed by browser implementers and game developers, and they were like, okay, we need this and this and this and this and this, and anyway, there was, in the end, this really great API that covers the needs of the game industry. And that's a great thing, because if you want to build your business on some platform, well, it's kind of cool that you can have a voice in the evolution of that platform. And last thing, the web is a trusted platform. So I said earlier that security is a big deal, and it's a big deal for us browser implementers. It means that when a web developer, web author generates a web page and it serves it to clients, we don't, as a browser implementer, I don't trust web pages. I need to sandbox everything and make sure that you can't do timing attacks and other kind of security issues. And there's a lot of engineering efforts that goes into making the web a secure place. And this effort goes into the design of the APIs and also in the implementations themselves. And what that gives you is the fact that, well, if you have two indie games, you don't know the authors, and one of them is a web game on a web page, you just click the link and start playing, and the other one is this binary on this website that you need to download and execute directly on your hardware. Which one are you more likely to try out? For most people, it's going to be the web game, because people trust web pages more than running arbitrary binary on their hardware. And this might change in the future if people understand that modern operating systems now do sandboxing of applications and stuff like this. But it's still pretty deep in people's mind. And we, as computer scientists, understand sandboxing, but users most probably don't. So the fact that the web is a trusted platform make it much easier for your game to get exposure, because more people will be, oh, okay, I'll check it out. And it's just one link away. The web is links, and that's kind of a beautiful thing. And web games, you don't need to install them, and that's kind of cool. I mean, that's another wall that you tear down. When you publish some game on the web, you may not force your users to install it, and I quite like this. And that's how the Firefox OS Marketplace is going to work in the near future. We're going to remove this install button and put a button that lets you start the application, start the game, the web page, the whatever, and then like from the application you can like, oh, I kind of like it, and then you click, I bookmark this, so I add this to my home screen or whatever. And I think it's a much better, much better system and model for application distribution. Now, my last remark is that the web is also open in that it doesn't force you to use a distribution mechanism. Your game can be just a link away. You can have app stores on the web, but there is not that one company that decides what game runs on the platform and what doesn't run on the platform because they don't accept you in their marketplace. And that, again, is a good thing for application developers and game developers, and more specifically, because you don't want to build your business on some platform that may someday decide that your game shouldn't be in the marketplace anymore, and then you get zero exposure. Not only zero exposure, but people just can't play your game anymore. That's the case on some platforms, especially mobile platforms. And that's something that at Mozilla we really don't want. We want an open web where everybody can publish things the way they like. And marketplaces should be services that help you get exposure. You might still want to go through a marketplace and abide to the marketplace's rule, but it's not something that should be enforced into how you distribute your games. So my conclusion is the web is the platform, and go make games, and I'll be happy to check them out on my phone, on my computer, and on my Firefox OS phone. If I still have some time left, I could show you a few things, a few demos. What time is it? Oh, I don't know how Mac works. Oh, it's different. Anyways, do I still have some time for demos? Great. Then it's going to take a few minutes because I don't know how the network's going to work and how this thing works. Yeah. All right, network. We'll see. In the meantime, if you have questions, you can start, and I'll try to kind of ask them as I work with getting the thing to load the page, because it doesn't look like. Give me a sec. It's okay. Any questions in the meantime? I have a few minutes. Yep. No, I'm more struggling with the network right now. Sorry about this. Demos are always like that.
Merci.
I'm listening.
Before you said that it is really hard to write ASM.js by hand, but is it possible to write simple JS and then compile it into ASM.js, and are there performance benefits for it?
So it's kind of a funny question, because the point of ASM.js is to have a representation where you have a lot of information that is useful for the compiler, for the JIT compiler to optimize the code. And of course, you could eventually write some tool that takes some JavaScript and generate some ASM.js code, and then run this ASM.js code. But the tool that would take the JavaScript and generate the ASM.js would actually have very little information about the code itself, and especially type information and things like this. And so you would, it wouldn't be able to do more than what the existing JavaScript virtual machines are already very good at. So I don't think there's really, it doesn't really make sense to take JavaScript and compile it to ASM.js, because then you kind of lose the point with ASM.js is that you directly write into something that has more information for the JIT compiler. So yes, you can, but I don't think that would be any useful, especially since a lot of effort goes into virtual machines. So the tool is probably not going to be as good as V8 or SpiderMonkey. Damn it.
So you want another question, or are you ready for the demo?
No, I'm struggling with of the network. Keep the questions flowing. Okay. Sorry about this.
Other question? Lunchtime, I think.
It's probably lunchtime, okay. Okay, sorry about this. I'll probably just, if you guys are interested in seeing some demos, I had very few of them actually, because the cool stuff is going to be at GDC. So come see me after the talk, and we can look at some stuff if you want. So thanks.
Thank you.
Thank you.